Hello and welcome to a new lecture through our deep learning course. Basically, before starting with coding the sentiment analysis or recurrent neural network, I need to go through some theoretical lecture regarding the word embedding, which basically give you some intuition of how this word embedding being instantiated and where we have go through. So without further ado, let's get started. Why actually we are going to embed our text? Because basically our machine doesn't understand nothing but a numerical vectors, and giving this text I need to generate whether this is a positive or a negative review. And so in that case I need to transform this review into a numerical vector. And in that case, our neural network will be learning the distribution of this vector and producing the resulting, whether it's a positive or negative. So the embedding is not that simple to transform just this text into any random vector, but it should be also taken into consideration that we need to here cluster our reviews into positive and negative. So the embedding should contain a meaningful interpretation whether this text is a positive or negative. So in the embedding space, if we geometrically interpret it or plot it, it should be having two separate clusters, the embedding itself. And in that manner, the neural network should learn the distribution of each cluster in this embedding space, in this sub-embedding space, and produce the result. Okay. So starting from the first approach, which is the bag of words. Bag of words is nothing but to count the existence or checking the existence of this token within such a document or within such a review. So for example, here I'm having this huge matrix, which will be a number of documents on the rows and number of tokens of the vocab on the columns. So each vector will be a huge vector for each document. So here I'm having this number indicating that the totally not satisfied review is being represented within the second document by placing digit 1 in this ith positions of this matrix. Okay, so this matrix will be holding this information of whether it exists or not, or it can be also counting the number of existence of this token within this document. Okay, so we have two different ways. Another thing is using this TF-IDF. So instead of counting the frequency or checking the existence, I can also give some improved way of giving each token a score in this document. So for example, here I'm giving a score totally to have a high score, which means like totally is indicating having some high information in its manner than the not, because not can be a low priority or low important token because it exists across many different tokens. And this is how TF-IDF generate its important scores. It is basically based on two equations, the TF and the IDF. The TF is term frequency. It just count how many times this term exists within this document, while the IDF, it counts how many times this term exists across all the documents. Okay, and multiplying both of them gives us the score of importance, which is a normalized somehow score. It is not so high or not so big or not so low, but it's a normalized in its manner. I'll be defining what I mean by now. So for example, here I'm having this simple comparison which between the IDF, that it will be on the level of all documents, and the TF would be on the level of single document. And the equation of both is pretty much simple. Here I'm counting the frequency, and here I am checking how many times this term exists across all the documents. So n is the total number of documents, okay? And I'm having here, if n is 5, okay, if I have 5 documents and this term existed across the whole 5 documents, okay, so I'm having here 5 over 5, so it will be 1. Log of 1 is 0. So this indicates that this term is having a very low importance. The score is pretty much low. So that's why the IDF here is a gate, somehow can be interpreted as a gate, because somehow can this document, can this token exist for too high number, like token not existed 35 times in this document, so it's pretty much important. But the IDF have a different opinion, like it say like the not existed across all the documents, so it doesn't have any indication that this token is having any meaningful interpretation, because it actually exists across all the documents. So if I remove it, I don't have any difference, okay? So that's why we can use the TF-IDF in stop words, obtaining the stop words in this language, because it will give the token which appeared in almost 90% of the documents a low score. So I can remove them from the corpus because they are stop words, more or less. And the other part, which will be counting the number of times the cat exists, it is here 30. So it's high, and also it didn't appear unless in 2 documents only. So it also have a high IDF score, which would be 0.4. So the TF-IDF, it will be 12, which is pretty much higher than the not. And if I calculated the TF-IDF for document 5, the cat in document 5, it would be 16. Okay? So more or less the advantage and disadvantage of this, it is very independent regarding the semantic meaning, because I can have a same token in different context, but this bag-of-4 or TF-IDF will give it the same embedding regardless of the context it exists within. Like for example, if I say I'm having a bank holiday today, and if I also said I'm going to the bank today, so bank here existed on the 2 sentences with a whole different meaning, and this embedding should be different as well. But the TF-IDF and Begoford, also the Word2Vec and the Glove, which will be discussed further after these slides, they will not be giving a different embedding. But the last language model, which called the Elmo Bird GPT, it will be holding this context information also. Okay, so for example, here I'm having a huge dimensional vector, like I'm having a vector with the same size of the vocab, which will be having some issues with the similarity score. So I'm having a curse of dimensionality issue, because when the dimensionality increases, I cannot calculate the similarity in a stable, efficient way. Okay, so it will be as well respectively slow for large corpus vocab, and the vectors also will be sparse. What do I mean by sparse? It means like it will be having a lot of zeros in its values, and so it will be large vector and sparse. Why sparse? Because the document will not hold all the vocab. Okay, so it will contain a lot of zeros, and as well the token will not be existing in all the documents. So the row and the columns will have a lot of zeros inside in the by definition. Okay, and but more or less they can be used as a baseline models. If you need to start your NLP project, you can use them. It is because actually they are pretty much fast, and apply any language model and any classification model upon this as a machine learning project. Okay, and also they can be used for obtaining the stop words, which is a good practice to generate them. Okay, and another thing is a more improved way of calculating the embedding is basically using these count-based methods, which more or less based on the matrix factorization, or the SVD, the singular value decomposition. And it started to minimize the reconstruction error between the original matrix and after factorization and removing some dimensionality from this original matrix, and generating or constructing the same dimensional, high dimensional matrix from this low dimensional space, and computing the error between them. I'll be discussing this singular matrix. uh, to be ranked. What do I mean by ranked? Like also, this will be holding the core information for each token, the first column values, which is a little bit different, a huge difference between it and the actual matrix, because the matrix here having its information distributed across the token, across all different tokens. But here actually I'm capturing the most crucial information within with respect to these specific tokens. Okay, and the information amount of information or amount of variance decreases gradually until reaching the last vector. Also the sigma here values, if we are going to look at its actual value, because this matrix is the diagonal matrix, so all the other two triangles here are going to be zero, only this diagonal will having values, and actually these values are ranked. Okay, this sigma 1 having the highest value and sigma n have the lowest value. It can be zero in sometimes. Okay, so what is the advantage of having these matrices ranked, or being the crucial information being ranked at the top? As we can see, the main objective here is that we can truncate these matrices. So I'm having a guarantee if I truncated only for a certain dimensions, I'm having a guarantee if I only cut this matrix into 10 vectors, like I'm having only 10 vectors here, I guarantee that these 10 vectors hold the most crucial information within this within this co-occurrence matrix. And the same as here and the same as here. Okay, so this can be as the dimension of the embedding now. So I don't need to have the same dimension of the co-occurrence matrix. I can truncate it. Okay, and in the same way, if I need to reconstruct this co-occurrence matrix from these low dimensional truncated matrices, I have this actually output, this x hat, which is the truncated version from the original matrix, and then I can calculate the reconstruction error. This is how the glove model, which we'll be discussing in the next slides, the glove model is based upon. So it's based upon this reconstruction error. It keeps iterating until it finds the best vectors having this low reconstruction error. And also it based upon the conditional probability of existence of a token with different tokens. I'll be discussing it in the next slide. So basically here, the main disadvantage of using SVD, it is expensive and not incremental. Basically the complexity of time here is W star, W squared, which is number of tokens squared multiplied by the dimensions that I'm choosing. Okay, so I have a large vocab. This will be too large actually to compute this SVD. But the main objective, the main advantage here, that these values will not be sparse anymore. So I'm having here a dense vector representing this token, okay, in a smaller dimension. This is the main objective of using SVD and have been used for a lot of decades. But after also, it's not incremental. Like if I have new data, I need to recompute it from scratch again. That's also another disadvantage. So what does the glove do here? The glove is basically counting the token's appearance with a context of a different token. Like for example, if I'm having 10 sentences, I need to find how many times this token I appeared with token J across all the each sentence within these 10 sentences. Okay, so for example here I reconstruct this co-occurrence matrix based on these instructions. How many times each token appeared in the context of a different token, and the context can be a sentence. Okay, so and I'm also checking within the conditional probability, like given an token I, what is the probability of token J to appear? So this is the language model. Okay, I need to predict what is the probability of a word cat given dog in the context. It's a high probability. What is the probability of having a giraffe in the context of having a different word of fridge? It is a very low probability. Okay, so that's what does a language model do? It learns the distribution of words given the context of them. So what is the probability of predicting a word J given the token I exists in the context? Okay, so the glove here actually does calculate this probability across the whole corpus. Okay, for example here I'm counting this joint probability, like I'm counting this fraction of number of times this token I existed within token J. how many times they exist together, and how many times the token I exists across the whole corpus. So this gives us the probability, the conditional probability that I need to predict the token, or to give the token J a probability of appearance. And another thing is to factorize actually these matrices, because they are in a huge dimensional, and apply this similarity upon these factorized matrices. So what do I mean by similarity? So basically, assuming that the similarity between two vectors is the same as the probability of appearance of this token with this token, with the context of another token. So if this token, for example, is I and this is the J, what is the probability of appearing this token J with I? Can I define it by the similarity of these two vectors from the truncated matrix? So can you understand the meaning, the intuition behind this? Actually, the enforced, the dot product, or the dot products, or this V transpose V, which is nothing but dot product between these two vectors, as the same as the probability, the conditional probability of J given I. So how much can this J appear given I is the same as the similarity between these two vectors. So this assumption is pretty much acceptable because they can be interrelated to each other. And equalizing them, they have inserted this log property, which I will be elaborate why. Basically, given this fraction, I'm here giving, I can write this probability into this difference between these two values, because the log is transforming into it. And this is the first equation I have. Okay, just bear with me. And similarly, the similarity between I and J is the same as the similarity between J and I. So I'm having this second equation by this two value. And adding these two equations, given that xij is the same as xji, I will be having 2 vij equal to log xij, log xi, and log xj. So basically, what is the main objective here? What is vi and vj? They are the representation. They are the representation of the tokens, which I don't have. This is the main objective. I need to find a good representation of the token V, of the VI, and a good representation for the VJ, by which the similarity between them, or the dot product between them, is similar or is close to the conditional probability xi and xij. So that's the objective. So if I can transform this equation into a minimization or optimization equation in the manner that the gradient descent objective is to generate vectors which will be having a good representation, by which the similarity between them, or the dot product between them, is pretty much close to the conditional probability, or this value, because this value I already have from this matrix, or the co-occurrence, or the factorized matrix, but this I don't have. So this actually is the main parameters I need to generate. So the objective here is to minimize, or to find Vi and Vj that minimizes this equation, which is based upon the dot product of these two vectors and the conditional probability value that I have from the co-occurrence matrix. And also I'm adding these two parameters to make it harder for the model to predict, or make it flexible for the model to find a best representation vectors for the VI and the VJ. Okay, I hope you understand this well. So now let's move upon different type of methods of embedding methods, which are the prediction based methods. It is basically based on the word of it. The previous one is based on minimization of the reconstruction error, but here it is the maximization of the likelihood of a corpus given its context. So I'll be describing what I mean. So if I have this embedding space, it should be a pretty much meaningful space. Like each dot here should be representing a token, and this token being close to another token should be meaning that this token have the similar or somehow close meanings to each other. So the embedding here is to have this semantic meaning across the words, okay? And the elegant way of the word of it that it also include or have the ability to apply linear equations or linear transformation on these vectors in that manner that if I remove the property of a man from the king properties and adding the woman property, I can have a result of the queen vector. So if I transformed the king, if I transformed the woman from the king and man, I would be having a queen. So that's very elegant actually how they transformed this word embedding into this simple linear equation and interpretable. So let's discuss how they have generated this meaningful embedding space. Basically, they have two approaches, the continuous back and forth or CBAO and the skipgram. They are pretty much interchangeable and can be used in an interchangeable way. I'll be discussing where exactly they can be used within. This is also the reference for the paper. It was, I remember it was generated on the 2013 or something. So basically, what is the continuous back and forth do? It have some context window. Like if I have a context window of 4 tokens, so I'm having 2 words before the target token and 2 words after it, and I need to predict what is the target word within this context. And if you can focus here, we have the main difference between the word of it and globe. So globe will be calculating across the global corpus, while here I'm having a context that I need to calculate upon. So this context is a hyperparameter, of course. I can increase or decrease, but it is not the whole corpus because the neural network should be predicting given this input value. Okay, and here I have this advantage that I can flexible control the embedding dimension, so I'm not enforced to have the same dimension of the vocab. Okay, so the size of the vocab is pretty much decreased. The different way, the other approach is the skipgram approach, which is basically giving the target word what is the context of it. So I'm having a different neural network objective here. I'm predicting the context instead of predicting the token. So if you can think a little bit why we have 2 different approaches, why we have this context as input and the other skipgram I have context as the output. So if you think a little bit, which one is the faster and which one is the slower? Of course, the skipgram will be slower because I need to predict a lot of words and I need to compute the loss and the gradient descent with respect to a lot of tokens. While here in the continuous back and forth, I have a single word to compute the loss upon. So in the CBOW, I'm having a less or a more an easier task than the skipgram. Okay, so this continuous back and forth is pretty much faster than a skipgram. So what is the benefit that I can use? So basically, if I have a large corpus, so I can use the continuous back and forth in that case, because I'm guaranteeing that this model will understand the corpus in a pretty much efficient way because I have a large corpus. So I will be having these interchangeable probabilities across all the corpus. So I don't need to bother with the skipgram. I don't need to predict the context. While if I have a small corpus, the skipgram can do the job here, can be much more efficient because it will be giving the token. I need to predict its context. So it's a more difficult task. So it will be enforcing the neural network to learn the distribution of the data that I'm giving it in a more efficient way than the continuous back and forth. Okay, I hope you understand the difference between both models. In a nutshell, what is the difference between globe and Word-to-Vec? As I have said, like the globe is a global co-occurrence, while the Word-to-Vec is a local co-occurrence embedding model. And also both of them doesn't consider the context of the token. If I have the same token but in different context, the Word-to-Vec, the globe, the bag of four, the TF-IDF, all will give the same embedding vector regardless of the context. So that's a main issue with this model. Lastly, another model have appeared which called the Elmo. And what I mean by Elmo here doesn't mean the Elmo in the Sami Street, but I mean the Elmo in the NLP field. And this is a good point that I have here. Like, based on the context, I should have a different embedding. So if I asked Elmo, what is the embedding of a word cat, it will tell me I need some context to give you the embedding. It cannot give you a simple embedding like Word-to-Vec, what is the embedding of king. So it will just give the embedding of it, which is the vector of 300 dimension or something like this. But the Elmo, it needs first a sentence to give you the embedding of a word king of any word. So basically, it is based upon two multi-layer backbone LSTMs, each of which will be in a bidirectional. So LSTM first one is the forward and the other one is in the backward. It will have the first input is the embedding, like it can be Word-to-Vec, can be Glove embedding, anything. It doesn't matter because it will be inserted in the forward propagation by the first stage, and after this it will be having this second layer of embedding. After the forward propagation, it will be inserted into the backward LSTM, and it will be give the last layer of embedding. And I will have these 3 layers of embedding, adding them each of which upon each other, which will be giving me the last embedding or the final embedding that I can use. So that's why the Elmo model gives the context an importance. So the backward and the forward actually digest the token context as much as possible and give a different interpretation from each direction. So as much as you can watch a movie for the first time and you have another one beside you who had watched the movie earlier, so he will be watching this scene, this specific scene. You will be having an interpretation of it, and he will have a different a total different interpretation because he has a different perspective or different view from his perspective. Okay, I hope you understand why Elmo giving this context based embedding and changing the embedding of the token based on the context, while the other doesn't do. So next lecture should be working on the sentiment analysis project running across the recurrent neural network end to end. See you there and goodbye. Thank you. Let's see you as well.